Hi everyone, I am Aravind, and today I'll be talking about our paper, A Moment Matching Approach to Testable Learning and a New Characterization of Rademacher Complexity. And this is joint work with Klivans and Pravesh Kothari. So let's dive straight into the setup. So the setup here is that of traditional agnostic learning in the sense of Valiant as well as Vapnik. So here we have a concept class C that's mapping a domain RD to labels, let's say plus or minus 1. And we have a joint distribution dxy on this domain across the labels. Given examples from this joint sort of label distribution, the learner's goal is to produce some hypothesis H such that the error of the hypothesis is close to the optimal error achievable by any function in the class C. So this quantity denoted opt. So you want error to be within opt plus epsilon. Okay, and a very sort of well established fact about this model at this point is that this task is unfortunately computationally hard, even in very simple settings, if you place no constraints on this joint distribution dxy. Okay, so traditionally the way people have dealt with this is to make certain assumptions, right? So at this point now, there's a large body of work on algorithms for agnostically learning various classes under distributional assumptions about the marginal. Right? It's common to assume, for example, that the marginal is the Gaussian or the uniform distribution on the hypercube, or log concave, or some other such assumption. So this marginal is denoted dx here. And this leads to an interesting question, right? If with no prior information about dxy, this joint distribution, how can you test whether your learner's guarantee actually holds? The issue is directly testing if your distribution is close to Gaussian or the uniform distribution in the hypercube, say, is computationally hard or even completely impossible or ill-posed. Moreover, you don't know the optimal error, right? So you cannot even use the simple procedure of validation, right? Where maybe you just run the training algorithm anyway, and you measure its test error on a holdout set and see if it looks close to what you expect, because you don't know what you should expect. You don't know opt, right? So with this sort of motivation in mind, there was this very nice model of testable learning that was recently introduced by Rubenfeld and Vasilyan, and which is also appearing at STOC this year. And in this model, you allow the input distribution to be totally arbitrary, and you sort of hope that the marginal distribution dx looks like a certain target distribution d star, such as the Gaussian, but you don't know this. Okay? And the goal is sort of to test just enough to guarantee that the learner succeeds. So this is what that looks like. So on the left, we have this traditional distribution-specific agnostic learning setup where you assume that the marginal is d star. So the learner L is getting examples from this distribution, and it manages to output a good classifier H. Okay, on the right, we have this new model of testable learning where the distribution is allowed to be arbitrary. Now, instead of just a learner L, you have a tester and a learner. Okay, and the tester now takes a sample and can either reject or accept. If it accepts, then the learner must be able to take these examples and actually produce a good classifier. Okay, so the tester T is certifying that the learner is able to succeed. And formally, for this to be sort of meaningful, we need the following two conditions: soundness and completeness. Okay, soundness says whenever the tester accepts, then the learner does manage to succeed, does obtain an error close to opt. And completeness says that whenever your original distributional assumption is met, so in this good case, when the marginal is in fact d star, then the tester should accept. Okay, so the tester cannot just always reject. So crisply, tester accepts implies learner succeeds, and dx equals d star implies tester accepts. So that's this new model of testable learning, which I think is a very clean and nice model. And with this definition, I can now say what the main contributions of our paper are. We basically answer some foundational questions about this new model. The first is to provide a full characterization of the sample complexity of testable learning using the Rademacher complexity. And then we also gave a broad algorithmic framework for testable learning using moment matching. Okay, so let's dive into the sample complexity aspect. So it turns out that sample complexity is tightly characterized by the so-called Rademacher complexity, okay, which is defined as follows. So the Rademacher complexity of the class C with respect to target distribution D star at size M is going to be sort of in expectation over a sample S drawn from D star that is randomly labeled. What is the best correlation that any function in your class C can achieve on this randomly labeled sample? Okay, so this is a very well studied quantity in statistical learning theory, and the main theorem that we get is the following. We get upper and lower bounds. The upper bound says that if little m is such that the Rademacher complexity at size m is at most order epsilon, then you can testably learn C with respect to D star using sample complexity little m. Okay, and the lower bound says if capital M is such that the Rademacher complexity at size capital M is at least omega epsilon, then testable learning requires sample complexity omega square root of capital M. Okay, so we see in this kind of way that the Rademacher complexity really provides nearly a full characterization up to this quadratic gap, which would be an interesting thing to resolve. And that's an open question. Okay, so now in terms of what goes into the proofs, I will not get into the upper bound too much because it's actually a fairly standard argument about sort of directly using the empirical Rademacher complexity. Instead, let's see what goes into the lower bound, which is, I think, more conceptually interesting. And the proof idea is basically to somehow define a distribution that the tester will accept, but the learner has no hope of succeeding on. So in this sense, you sort of fool the tester-learner pair. Okay, so the way we do this is suppose that the Rademacher complexity at size capital M is in fact large. Okay, say it's in fact say close to 1, which is the largest possible. What this means is that with high probability over a sample drawn from D star of size capital M and a random labeling of this sample, there is some function in C that is approximately consistent with this labeling. Okay, because that's exactly what the Rademacher complexity is measuring. And what this means is that if you define dxy, this new distribution, to be uniform over this randomly labeled sample, then by construction the optimal error is small. Right? That's basically what it means for the Rademacher complexity to be large. With high probability, this will be true. Okay, now so sort of pictorially we can imagine this big sample S that's randomly labeled. And suppose now that the tester learner only gets a small subsample, essentially a small sample S prime of size little o of square root m drawn from this distribution dxy. The thing is, this S prime will have marginal that is statistically indistinguishable from a sample of the same size if you drew it from a distribution actually with marginal D star. Okay, why is this? Basically because if you don't draw the same sample of S twice, essentially you have no way of knowing that this sample did not come directly from a distribution with marginal D star. Okay, and you can formalize this using the collision probability, and this is where this little o of square root m comes in. The collision probability, sort of the probability of drawing two of the same guys from S, is going to be little o of 1, which is like negligible. And so the tester is forced to accept, right? The tester, basically any tester that accepts when the marginal is actually D star will also accept in this case. But the learner cannot hope to do well on the labels that it hasn't seen, right? Because the labels are random. And this S prime is just a small fraction of S. So the true error on the distribution will be close to 1/2, which we know is much bigger than the actual optimal error. So in this way, we have forced the tester learner to fail. And this is basically how we get the lower bound. Okay, so why is this sort of interesting now? I think one of the key reasons is that it has a close relationship to this basic paradigm of uniform convergence in statistical learning theory, right? By which, for our purposes, I mean that the empirical error on a sample of size m is close to the true error over the distribution uniformly over the entire class C. Okay, that's what I sort of mean by uniform convergence here. And a very classic result in learning theory is that in the setting of distribution-free supervised learning, the sample complexity is fully characterized by the VC dimension, which also characterizes uniform convergence tightly, okay, in the distribution-free uniform convergence. And so we see that in this setting, uniform convergence is both necessary and sufficient for learning. Meanwhile, for distribution-specific learning, it turns out that the sample complexity is actually characterized instead by the L1 metric entropy, or the log covering number with respect to the L1 metric induced by that distribution. And here it turns out that while uniform convergence is sort of always sufficient, it's actually not necessary. And there's counter examples such as convex sets in Gaussian space, where you can actually learn using sample complexity that is much better than what you would need to ensure uniform convergence. So I think that's interesting. And then testable learning now really adds to this landscape in a new way because it's characterized by the Rademacher complexity. So first of all, it's different from distribution-specific learning. And moreover, the Rademacher complexity is known to tightly characterize uniform convergence in this sense, distribution-specific uniform convergence now. And so again, we see that uniform convergence is necessary and sufficient for testable learning. So I think this is one of the key reasons why this statistical characterization is conceptually quite interesting. Okay, cool. So now let's get into the main sort of algorithmic results in this work. So the main theorem that we have is the following. It says that if the concept class C admits degree k sandwiching polynomials with respect to D star. Okay, so now sandwiching approximation is a slightly stronger notion of approximation than standard L1 approximation. And it says that for any function f in the class, there must exist degree k polynomials, let's say PL and PU, such that PL and PU upper and lower bound f pointwise over the entire domain. And they satisfy this nice approximation guarantee, which is that the L1 error, in this case, you don't even need an absolute value. This L1 error is at most epsilon for each of them. So it's this kind of strong two-sided kind of L1 approximation. And we also require such polynomials to exist with sufficiently small coefficients. Okay, and the quantitative dependence, I think, will be clearer in subsequent slides. So if this holds, then you can testably learn the class C with respect to target distribution D star in time that is D to the order K. Okay, so that's the main algorithmic result. And let me mention that here the tester is quite simple. It just checks that the degree K empirical moments match those of the distribution D star of the target distribution. Okay, so it's in fact completely label oblivious. One application of this result is an algorithm when C is the class of half spaces and D star is, say, the Gaussian or the uniform distribution on the hypercube, then we actually obtain an algorithm that takes time D to the order 1 over epsilon squared. Okay, so this is sort of actually the best possible result you can hope for because it matches known lower bounds for this problem even in the ordinary agnostic setting. Okay, cool. So let's say a bit now about how we obtain this result and also just put it into context a little bit. So the starting point is this classic result of KKMS, which showed a generic approach to agnostic learning. They showed that whenever the class C admits degree K L1 polynomial approximators over this distribution d star, then you can agnostically learn in time d to the order k, assuming that the marginal is in fact d star. Okay. In our setting, of course, the key issue is that, sure, d star, which is say the Gaussian, might be nice in this way, but how can you test that the unknown distribution that we actually have, the unknown marginal dx, also admits such approximators? And the way we'll do this is we'll show a somewhat generic transfer lemma. We'll show that if d star admits sandwiching polynomials, sandwiching approximators, and dx matches low degree moments with d star, then these sandwiching approximators for d star also are valid sandwiching approximators under dx. Okay, so that's the type of transfer lemma that we'll use. And I should mention that this is not true for ordinary L1 approximation. You will not just have this kind of transfer lemma, and this is one of the key sort of reasons why sandwiching enters the picture for this type of result. And I think now with this, you can really see our main result as an analog of this generic framework of KKMS. They showed that whenever you have L1 approximation, you can agnostically learn. We are showing that whenever you have sandwiching approximation, you can testably learn. And one of the interesting things about this is that this actually matches the best known bounds for even ordinary agnostic learning in many cases, because in many cases, the way that you actually construct these polynomials, L1 approximating polynomials, is in fact by directly constructing sandwiching polynomials. Okay, so cool. So let's now get into one of the key ingredients that goes into this whole setup, this framework, which is that of duality, which is an important thing for all sorts of considerations about sandwiching polynomials. So first, a definition. For brevity, let's say that dx delta k moment matches d star if all the degree k moments of dx are within those of d star up to an error of delta. Now here's the big theorem, and this is actually a generalization of a very basic result in pseudo-randomness due to Bazzi, and which was generalized in a different direction by Klivans and Meka in 2013. It says that the following are equivalent. The first is approximate moment matching fools the class C with respect to D star. What does this mean? It means for any f in C and any distribution dx that delta k moment matches D star, we have this fooling result. The bias of f under dx and the bias of f under d star are close within epsilon. And this is equivalent to the existence of sandwiching polynomials with small coefficients for C with respect to d star. Okay, that is, for any function f, there must exist degree k sandwiching polynomials that satisfy the slightly stronger kind of approximation. Okay, so here what this can be interpreted as saying is that not only should the approximation error be order epsilon, but also the coefficient, so this is the L1 norm of the coefficients of PL, this must also be order epsilon when you multiply by delta. Okay, so this is the precise sense in which the coefficients cannot be too large, okay, formally. And of course, similarly for PU. So this is the duality result. Okay, so let's zoom out now for a second to see where this duality result fits into our overall roadmap. So we just saw this equivalence between approximate moment matching fooling the class C and the existence of sandwiching polynomials with small coefficients. And now it's sort of actually easy to show as a corollary the kind of transfer lemma that I was referring to, where sandwiching polynomials under D star translate directly into sandwiching polynomials with respect to any dx that approximately moment matches D star. Okay. And now once you have this, it's immediate that you can just use polynomial regression, the classic approach of KKMS, to actually obtain testable learning. Because what you'll do is just test that the true unknown marginal moment matches the target, and then you're guaranteed that polynomial regression will succeed because these sandwiching polynomials exist. So now the key question becomes, how can we actually instantiate this whole framework? right? So when is it actually the case that approximate moment matching fools certain classes C with respect to certain distributions D star? So actually, let's begin with the setting of the hypercube, in which case this whole framework becomes very simple. Let's fix D star to be the uniform distribution over the hypercube. For many classes C, such as half spaces and AC0 circuits, KY's independence is known to fool these classes. Right? These are very basic results in pseudo-randomness and complexity theory. For example, for half spaces, the degree K that you need is order 1 over epsilon squared for epsilon fooling. Moreover, you have this very powerful result due to Alon et al. That says that any distribution that is almost K-wise independent, meaning its degree K moments or biases are almost zero, such a distribution is close in TV to an actual K-wise independent distribution. And this sort of directly gives you that almost K-wise independence fools these classes C. In the setting of the hypercube, almost K-wise independence is the same thing as approximate moment matching. So this is exactly what we were looking for. Now, moving to our more general result, for half spaces, it looks as follows. The key structural theorem is the following. Approximate moment matching fools half spaces. Right? So let's fix D star to be a strongly log concave distribution, meaning that the density of the distribution is strongly log concave. The log of the density is strongly concave. And let C be the class of half spaces for now. Let's fix these parameters K and delta, K to be order 1 over epsilon squared and D to be delta to be D to the minus order K. And delta is not super important for the purposes of conveying the main idea. Now, for any distribution dx that delta K moment matches D star, we have the main fooling result. We have epsilon fooling. And let me mention that a big part of the interest of this result is that it actually extends more generally, not just to half spaces, but functions of a constant number of half spaces, like intersections of half spaces, as well as more general distributions that satisfy some concentration and anti-concentration properties. It doesn't need to be a strongly log concave distribution. It doesn't need to be just the Gaussian or anything. Cool. So how do we prove this? Let me try to convey the key ideas that go into it. The key idea really is to relate various probability metrics in a systematic way. Okay, so let's suppose that D star is in fact strongly log concave and dx delta K moment matches D star. And you can actually now show the closeness of the corresponding characteristic functions, which are defined as follows, right? It's the expectation of e to the I times v dot x. And you can show closeness using a sort of careful Taylor series argument by expanding up to degree K. And this will crucially use the fact that the derivatives of these characteristic functions encode the moments, right? And this is very natural because the characteristic functions are precisely the complex valued analogs of the moment generating functions. And now, once you have closeness of the characteristic functions, you can translate this to closeness in Levy distance and then closeness to CDF distance. So closeness in these more standard probability metrics using existing tools. And this sort of scheme sometimes goes by the name of the method of distances in probability. And this was also used in this nice prior work of Klivans and Maker. So closeness in CDF distance is finally enough to actually give us the main fooling result that we want for half spaces, as well as functions of half spaces, it turns out. So great, so that's the key idea. So now coming back to the roadmap, this is basically how we finally obtain that for the class of half spaces and functions of half spaces and D star being a log concave, strongly log concave distribution, we get testable learning. Okay, using moment matching and then just polynomial regression. Cool. So that's our main results. With that, let me move to some open questions. I think testable learning as a framework is applicable kind of broadly in a lot of machine learning scenarios wherever assumptions are hard to test and direct validation is not easy. It's sort of closely related to this classical problem of model selection in statistics, except now you're also allowed to reject. So there's many interesting directions to pursue. You can generally ask what other classes can we learn, what other types of guarantees other than accuracy can you test. One natural question is, can you design fully polynomial time algorithms for the case of half spaces? We saw algorithms that required time d to the order 1 over epsilon squared, which is still exponential in 1 over epsilon. So can you somehow achieve a different trade-off and get fully poly time? Moreover, can you design testers that are not tailored to a single distribution d star in the way that these moment matching tests are, and instead accept a wide class of distributions, such as all log concave distributions? And I'm happy to say that at least for half spaces, in forthcoming work with a bunch of amazing co-authors, we are able to answer both of these latter two questions affirmatively. So, cool. With that, I will stop. Thanks a lot for your interest.